So I welcome all of you to IIT Bombay's virtual competitive algebra seminar. It's a great pleasure to have Dan Katz from University of Kansas. He will speak on Rees Valuations. But I want to tell everyone in this audience that Dan Katz has many friends in our department and also those who are attending this seminar. In fact, my first job was in Lawrence, and Dan was my mentor. We collaborated a lot. We discussed a lot of mathematics, and I learned how to collaborate with people. First time I was writing papers alone, and it became fun to collaborate once I discussed mathematics with Dan. We will have two lectures by Dan on Rees Valuations. It's a favorite topic for all of us, and Dan is an expert on this. I think he has a expository article also on Rees Valuation somewhere. I'll try to find out.
Yeah.
But you can find Rees Valuations in many of his papers, and in these two lectures, we will learn the basics and some recent applications of Rees Valuations. So over to you, Dan.
Okay. Well, thank you, Jugal. I'm glad to participate. Thanks for asking me. And as Jugal alluded to, these are expository lectures. So, I mean, it's going to be somewhat like preaching to the choir. Just during the lecture, I'm going to turn my camera off, and just because I move around a lot, and then I'll turn it back on. So, all right, so throughout R is an Ethereum ring, and I contained in R an ideal, and the height of I. I'll always assume that the height of I is bigger than 0. You can develop the theory without that assumption, but it's just more convenient and you get a little bit better results. And so the whole point is that there exist finitely many valuations on R. That capture many asymptotic properties of the ideal. And so a little bit of history. Again, older people know this, maybe some of the younger people don't, perhaps, but in the early 1950s, actually, in 1952, Pierre Samuel wrote a paper in the Annals of Mathematics called On Some Asymptotic Properties of Powers of Ideals. And in that paper, he studied different properties of the powers of ideals and especially containments among them, and with some familiar identities. And so his basic assumption was that he had two ideals, I and J, with the same radical, so that the powers are cofinal. So of course that means for any n, some power of j is contained in I to the n, and for any m, some power of I is contained in I to the m. And he defined two functions, and I'm just going to mention one of them because that's the one that's relevant to Rees valuations. So Samuel defined the following. He defined Vijn to be the largest exponent such that j to the n is contained in I, V, I, j, n. So j to the n is contained in this power of I, but not any larger power of I. And then he defined a limit, which he called Lij. Of V, I, j, n over n. And similarly, he defined another function where you take I to the n and you take the least power of j that lands inside of there. And there was a nice interconnection between those two functions. And he defined limits and proved all sorts of interesting things about the corresponding limits. In particular, the product of those two limits were 1. And then he used those limits to define something he called asymptotic equivalence or projective equivalence, which after the fact turned out to be related to integral closures of ideals and powers of ideals. He asked a number of questions in that paper, and 2 of them were the following. Was that first limit Lij rational? Sorry, it's too early for me to have good handwriting. And then he asked, are the deviations? Oops, it should be Lij. Bounded. He actually asked a couple of other questions too, but these are the ones that had a positive answer. And in response to Samuel's paper, there were several responses. One of them was Muley. He elaborated on the results and drew a connection. Whoops, sorry. In order for you to see comfortably, I have to keep shifting the paper. And he drew connections with integral closure. And then independently, Mcadam and Reese answered the questions positively. To both questions. But what Reese did, and Reese recast the questions, well, recast actually the work. In terms of pseudo valuations and just valuations. Let me see, maybe I'll make this just a little bit bigger, but then I have to keep shifting the paper more. Okay, and he used the following definitions. The first, and they're familiar to everyone by now, of course. For X and R, you write VIXT if X is in the tth power of I, but not the t plus first power. And of course, we allow t equal to b infinity. R is an arbitrary Noetherian ring, not necessarily local. And then V bar I of X is the limit as n goes to infinity. Vi of X to the n over n. And the thing to note here is that Vi of X is just Samuel's Vi XRn. it's just the case when J is principal and B bar I of X is Samuel's limit when J is principal. And Reese noted that you can just work with these functions and this limit as well. Okay, and so what did Reese prove? What we call now the Rees Valuation theorem. Namely, that there exists a finite set of valuations. They're really discrete valuations, but they can take the value infinity, V1 through, say, VR, and R, and positive integers. E1 through EK, such that 1 this limit Vi bar of X is the minimum over I, Vi X over EI, and 2 for each I, the set of X in R such that Vi of X is infinity is a minimal prime. And as we'll see in a minute, and just about everybody knows, of course, when you define Rees valuations and construct the rings, you just note that if you're not in the domain case, you get the things that are inherited from the case when you mod out minimal primes. So anyway, these VIs, of course, V1 through VK, these are the Rees valuations. And then the associated DVRs. Are the Rees valuation rings. Okay, so he also proved what's called the strong valuation theorem. In the case when RM is analytically unramified. If you're in the local case. So. Then there's an integer depending upon I, such that this difference, Vi bar of X minus Vi of X, is less than or equal to Ti. Here you can, well, Rees historically first considered the domain case, and many of these things reduce to the domain case. This is true for all X, not if you're in the domain,
sir?
Yeah.
Excuse me, can you please shift the sheet a little down?
Oh.
We are unable to see the first line.
Sorry, yeah.
Thank you.
Yeah, that's the problem. If I magnify it enough so that it's comfortable to see, then I only capture about 2/3 of the page. Okay, so these results were carried out in a series of 4 papers, and they kept being refined because, well, he was seeing and understanding the situation better. And moreover, initially, the full version of the Mori-Nagata theorem wasn't proven when Rees initially started thinking about this, or at least he wasn't aware of it. In other words, that the integral closure of a Noetherian integral domain is a Kroll domain. So he kept refining the results, and after the 4 valuation papers in which he discussed the valuation theorem, he proved a couple more papers strengthening the characterizations of analytically independence. So I won't talk about those, but anyway, this is how Rees Valuations came about in answer to Samuel's questions. And so let's assume R is a domain, because that's the essential case. You take a finite set of generators, and then we'll set Ti to be the R algebra obtained by joining the fractions x1 over xi through xd over xi. And henceforth, if I've denoted a set of generators and I write Ti, I mean the birational algebra attained by joining the fractions in the generators that have I in the denominator. And of course, the thing to note is that I times Ti is just the principal ideal generated by X. Now each Ti bar is a Kroll domain. So what does that tell you? It means Xi times Ti bar is contained in finitely many height 1 primes. P1 through, I don't know, P, K. And moreover, if you localize each Ti bar, I guess I should say I1 there, okay. Localized to Pij, Bij is a DVR. In other words, with I fixed, Bij, these are what we call the essential valuations of Ti bar containing IT. And then these are the Rees. Oh. And then if you collect them all, these are the Rees valuation rings. So this is one way to construct the Rees valuation rings. You form these birational algebras, you look at the integral closure, you take the essential valuations that actually, if I say it this way, it's the essential valuations of not containing Ti, but such that you say it this way, IV is not V. Anyway, the terminology in the theory of Kroll domains, the essential valuations are just the DVRs you get by localizing at the height 1 primes. So, of course, there's another construction. Oops, okay. You take R to be what we now call the extended Rees algebra. And I'm still in the domain case, say. And then we let V1, maybe I should use W1 through WT, say. These are the essential valuations of the integral closure for which T inverse W. In other words, take the integral closure of the Rees ring, look at the finitely many height 1 primes containing T inverse and localize. Okay, and then now set Vi equal to Wi intersect the quotient field of R. And Vi. Then the Rees valuations can be obtained this way. So this is an alternate way of obtaining the Rees valuation rings. Just a quick aside, it's funny how history works, that we now call this ring without the T inverse the Rees algebra, and we call this ring the extended Rees algebra, when in fact, historically, if I'm not incorrect, Rees was a great admirer of Zariski, and Zariski more or less introduced this algebra. And in studying the valuation theorem, Rees cleverly introduced a T inverse, which allowed him to reduce the general case to the case of a principal ideal. And so this is the algebra that was introduced by Rees. And so historically, one might think you should call this the Rees algebra. But I'm not one to buck modern trends. We call this the extended Rees algebra, but you should note that this is the algebra introduced by Rees. Anyway, so this is another way of capturing or describing Rees algebras. And then if R is not a domain, you just pass to the minimal primes. Then we think of the Rees algebra as the union over Q in min spec R. The Rees algebras of I extended to R mod Q. Okay, now what's nice is sometimes a single affine cover works. Oops, sorry. So for example, here's something, a result of Judy Sally. Suppose the ideal that you're working with is a system of parameters in the local ring Rm, and R is quasi-unmixed. I'll use that abbreviation for quasi-unmixed. Now let's set S1 to be T1 localized at MT1. So in this case, when the elements are analytically independent, the maximal ideal will extend to a prime ideal. And of course, in this case, this is a one-dimensional local domain. But let's say we're in the domain case. Then the Rees valuations are the Rees valuations of IS1. And they're actually the essential valuations of S1 for such that, well, essential valuations V such that IB is not V. So not only do you have one affine cover, you actually get to localize first. They all appear here. The quasi-mixed assumption is crucial. That prevents, the quasi-mixed assumption prevents the following from happening. When you have T, one of the TIs, say, and TI bar, and then you have one of the Rees valuations. This corresponds to a height 1 prime in the integral closure. The quasi-mixed assumption guarantees that when you contract back to T itself, it too has height 1. The quasi-mixed assumption is the same as the altitude formula. Okay, in any case, sometimes you can have an affine, single affine cover. Another example is if R contains an infinite field, and A and I is sufficiently general. Then V of I are just the valuations associated to just the single piece. The problem here is this is a sufficiently general element and it's a little bit harder to describe. Okay, a couple other basic properties. I'll define integral closure in a minute, though it's hard to imagine that everybody doesn't know what integral closure is. But the Rees valuations of I are the Rees valuations taking integral closure, and the Rees valuations of I to the n, and the Rees valuations of I to the n. And for if U contained in R is multiplicatively closed, then the Rees valuation, I keep saying Rees valuations when I mean Rees valuation rings, but it's essentially equivalent. These are the rings such that when you intersect the maximal ideal of the DVR with R, it's empty. So it's exactly what you would expect. All right, so what's the connection with integral closure and to analytic spread? Okay, so definition, I bar, of course, is a set of X and R such that X satisfies a familiar equation. Okay, and of course that's an ideal. Even in the non-Noetherian case, here's the following standard fact. And again, this is the case, R is a domain. Namely, the integral closure is the intersection over, you can put the parentheses anywhere, these are over all valuation domains. So Noetherian, discrete or not, the integral closure is you extend to every valuation domain and contract back. Every valuation domain between the ring and its quotient field. But with Rees valuations, you can do better. In the Noetherian case, you can do better. So how do you do better? So take the Rees valuations. For all n, I to the n is the intersection of I to the n be I intersect. So you just get to use finitely many Rees valuations to take the integral closure, capture the integral closure. And let's see a quick proof of this. Okay, so, sorry. Suppose x is in I to the n bar. So that means x is in the integral closure here. Oops, this is some vi. Okay. But this is a principal ideal. Say, I didn't specify some generators. So it's just, sorry, it's a to the n vi. Bar, but then that means x over a to the n is integral over vi, but DVRs are integrally closed, so x over a to the n is in vi, so x is in a to the n vi equals I to the n vi. And then conversely, suppose here we'll take some generators. I is generated by these elements, and suppose W is an evaluation ring in the quotient field. You take y, the intersection of the powers, the nth power, extended to the Rees valuations. Okay, then what do we know? We know that Ti is contained in W for some I. Maybe I'll call that J. Tj is contained in W for some J. This is the fractions in the generators with xj in the denominator. So if you, what's the best way to say it? So y is in the intersection of the xi to the n vj, where the vj's are the essential valuations of T, what am I calling it? Tj. We go from here to here. Tj bar containing xi. All right, so what that means then is if you use the this basic facts about Kroll domains, that means keep getting that. That means this. So you take the finitely many DVRs over Tj bar that for which the extension of x sub j is not a unit. And if an element is in the intersection of those, this is why they're called essential, it's then in the ideal generated inside of the Kroll domain. But this is I to the n Ti bar, and this is contained in I to the n W. So this is y is in the intersection I to the n W, which is I to the n. Anyway, it's just a little calculation using basic facts about Kroll domains and valuations. All right, so an interesting fact here is what follows is that if you look at the union over n of the associated primes of R mod I to the n bar, this is, if you take the centers of the Rees valuations, those, you get that union. So these are sometimes called the asymptotic primes. Of I. Okay, and then of course, lots of work has been done studying these. Actually, this is an increasing, as you let n vary, this is an increasing set and it's finite. So it actually stabilizes. Well, of course, it's finite because of this. Okay, so what's the connection with analytic spread? Well, so here R has to be local. So the analytic spread is what? It's the dimension of the fiber ring and it's the fewest number of elements generating a minimal reduction. Okay. Of I. This is, of course, you have to assume the residue field is infinite. Okay, and so there's a well-known theorem of Mcadam that can be stated this way. Let's just assume R is a domain. So the Rees valuations, the Rees valuation rings are nearby. Then P a prime ideal. Then 1. The analytic spread of IP is the dimension. If it is the dimension, that implies that P is the center of a Rees valuation. And then 2, the converse of R is quasi-mixed, then P is the center. The Rees valuation implies analytic spread of IP is then RP. So here we see that the Rees valuations are asserting some influence over the local analytic spread. So for example, this would say that for a quasi-mixed local ring, the analytic spread the ideal has maximal analytic spread if and only if the maximal ideal is the center of a Rees valuation. Okay. Well, not every ring is quasi-mixed, and sometimes you can get away with things in the non-quasi-mixed rings by looking at particular Rees valuations. So I like to follow Reese's terminology, but maybe it's old-fashioned. So suppose you have a local, and let's just say this is a local domain of dimension D, and V is a DVR in the quotient field of R. Actually, it's contained, it's trapped between the two. Then V is an M valuation. And the common term is divisorial if, well, MV intersect R is M, so it's centered on M, and then the transcendence degree over the residue field. This is the residue field of the valuation, right, is D minus 1. And now let's set Vm of I to be the Rees valuations that are M valuations. And then in the non-domain case, just do the usual thing. The M of I is the union over Q. These are the minimal primes. The M R mod Q. And here I still want to take M valuations that have residual transcendence degree D minus 1. If you're not quasi-mixed, then you're not necessarily, so here. I mean, it's sort of implied, because I still want these to correspond to the dimension D case. And for example, if R is quasi-unmixed, then every Rees valuation centered on M is an M valuation. Okay, let's see. Trying to gauge the amount of time left here. All right, well, there's a nice connection that probably, certainly known to Reese, but never written down. As far as I know, this is something that Javid Valadashti and I used in our paper on Rees valuations. Let's assume, say, Rm is a local domain. Everything always reduces to the domain case. Dim R equals D. Then that implies Li. The analytic spread is D, if and only if there's at least one M valuation. And in the second talk, we'll see that both for work of Reese and some work of Javid in mind, it's the M valuations that exert the most influence on the asymptotic properties of the ideal, especially, say, in terms of things like multiplicity in the case where the ideal is M primary, and J multiplicity in the case where the ideal is not M primary. And I don't know, I was going to prove this because it's not difficult. Let me see if I have enough time. So, sketch of the proof. Let's assume we're in the domain case. The field is, let's suppose the analytic spread of I is D. And we can assume that I is generated by D elements by replacing I by a minimal reduction. Then MT1 is a height 1 prime. Remember what T1 is. That's because of the generators are analytically independent. And then the images of x2 over x1 through xd over x1 in T1 mod M T1 are algebraically independent. Okay, again, that's another consequence of the analytic independence. Okay, so what we do now is take P contained in T1 bar, height 1 prime, lying over MT1. Well, that of course by construction means that if I take V to be T1 bar localized at P, this is a Rees valuation. And we have K contained in T mod MT1, which is contained in T1 bar mod P. So because of the analytic independence, this is D minus 1. But this part is integral or algebraic, however you want to say it. And of course, this is the quotient field of this is just K and B. So that means that residual transcendence, that means the residual transcendence degree here is D minus 1. So V is not only a Rees valuation, it's an M valuation. Okay, let's see, the converse is similar in spirit. If you take, suppose V is in Vm of I, and you let x1 through xs be a minimal reduction of I. So we can assume I is, we can replace I by a minimal reduction and assume it's generated by these guys. Oops, sorry. Okay. Okay. And then by definition, V is Ti bar localized at some height 1 P. That's what it means to be a Rees valuation. This is, but we don't know which I, so it's for some I. And so now we have K contained in, we have the residue field here, MV intersect Ti. This is a prime, so you mod it out from Ti and take the quotient field. And you have K and V. So as before, this part is an algebraic extension. This part has transcendence degree D minus 1. Okay, so that means the transcendence degree, this is over K, of K MV intersect Ti is D minus 1. Sorry, I'm hurrying up a little bit here. But that means that's same as, that's the quotient field of Ti mod MTI. But this is an algebra, finitely generated algebra over field. So that means the ring dim mod Ti mod M Ti is d minus 1, but sorry, my mistake, not yet. This is mv intersect ti. Sorry about that. This is dim t mod mv intersect ti, d minus 1. So that forces, because of dimensions here, that forces mv intersect ti to have height 1. But by the analytic independence, m ti is a prime. It's certainly contained in here. So that forces the height of mti to be 1. Okay, so that means sorry. Okay, I've still got time. I'll slow down. So that means mti is mv intersect ti. But s minus 1 is the transcendence degree over k of ti mod mti. But then that's the transcendence degree over k of t mod mv intersect ti, which is d minus 1. So s is d. So ideals with maximal analytic spread are precisely those ideals that have an m valuation, which a Rees valuation that is an m valuation. Okay, and that'll be crucial because the theme of sort of what the paper by Javid and myself is that in many ways, what you can do for Rees valuations and multiplicities for m-primary ideals can be recovered for ideals with maximal analytic spread and using m valuations. And that'll, in the second talk, that'll become more clear. So a corollary of this is the earlier result of Judy Sally's that we mentioned. If you take an ideal of maximal analytic spread, and you take a minimal reduction, again, assuming then the Rees, I'm sorry, then before, if you remember, she had an m primary idea. Then the m valuations that are Rees valuations are the essential valuations of T1. Okay. And then finally, I'll state a theorem that Javid and I proved that talks about how the connection between Rees valuations of this type, well, and over a local ring and to completion. So, theorem. I guess this is a special case of the theorem. We proved two theorems, JV plus dk. So let's suppose R and K is local. Sorry about that. The analytic spread of I is D. Then there exists a one-to-one onto correspondence between V, M, I, and V, M. So this is really the maximal ideal in the completion. So how is that given? as follows. So if you take W in the M valuations that are Rees valuations, sorry, I want to take in the completion here. Then by definition, W is in VM I times R hat mod Z for some Z and min spec R hat. So you more or less do the obvious thing. You just have to prove that the output is a Rees valuation. That's an M valuation. Okay. Then for Q equal to Z intersect R. So you contract that back to the base ring. Then we have R mod Q, and then you intersect W with the quotient field R mod Q. And then we show that this is in V. And if I call that V, then, whoops, I'm sorry. Then moreover, the completions are the same. And then we have a global version of this that doesn't require maximal analytic spread. So the idea is you take your element in VM, it corresponds to something in the quotient field of R hat mod Z for minimal prime in the completion. And so you basically contract that back to the quotient field of R mod Q, and that's a V. It's certainly a DVR. And then you argue that it's in VM. And then I like to think of the minimal primes in the completion for which the ideal has maximal analytic spread as parameterizing these guys. So the picture I like to draw, and it's in the paper, is if you let Z1 through ZH be the min primes in R hat, such that the analytic spread of I times R hat mod Z is D. Then draw a better picture. Oops. Here. So have the minimal primes such that the analytic spread of the ideal is D. These are the minimal primes in the completion. Then up here you have your discrete valuation rings. Let's say T1, WH, WHTH. And now you have the DVRs associated to the original ring, the base ring. Oops. And so the picture looks like this. So I like to think of the minimal primes in the completion for which, when you extend the ideal, the analytic spread is D. And so over the quotient field, you have these finitely many elements and these finitely many elements over the different quotient fields. And altogether, they give you VM of IR hat. And then when you intersect them to the corresponding quotient fields determined by the minimal primes here, then you have this picture. Okay, so I'll stop.
Great. Thank you, Dan. If there are any questions, you can open your mic and video and ask any questions you have.
I mean, this is all pretty much well known. So next time then I'll talk about connections with multiplicities. There's the original connections determined by Reese, and then some results, proven by Javid and myself that show you can recover a lot of things that you can do in regards to Rees valuations and multiplicities for M-primary ideals. They can be extended using ideals of maximal analytic spread and J multiplicity.
Yeah. In this last result with Javid, you have this one-to-one correspondence with M valuations. Suppose you have an ideal of, equimultiple ideal instead of M primary ideal.
Okay.
Do you expect a similar result for when the centers are, say, the equimultiple ideal has just one minimal prime?
Actually, there's a more general statement that doesn't have any conditions on the ideal.
Okay.
So what you do, and you can make it a global statement. So the idea is, let me put the screen back. I mean, what happens is, I mean, you just start with a prime P containing I. And, let's see. Well, and the idea is that you have the Rees valuations. These are the Rees valuations of I centered on P. And then you have the Rees valuations of, sorry. And you don't need any, you still get a one-to-one correspondence like this. And the more general result doesn't require maximal analytic spread. But then what happens is, in the local case, you, instead of having the Z's here with maximal analytic spread, you have families of Z's determined by the analytic spread of the ideal extended to the completion. So you can make a general statement that doesn't have any conditions on the ideal. You just have to, instead of looking at I should have just stated the local case. In the local case, you just look at all the possible analytic spreads modulo minimal primes in the completion. And then you write down a similar correspondence.
Okay.
But yeah, I mean, that's the natural way of generalizing an M-primary ideal is equimultiple. But actually, we don't have to go so far. We just think of maximal analytic spread.
Yeah.
Or locally maximal analytic spread. So.
Yeah, I don't see any questions from audience. So anyway, we can formally close the meeting. People who want to stay back and talk informally can stay. Otherwise, we meet next Friday at the same time.
Okay.
Yeah.
Sounds